Stephen Hawking calculated that black holes erase 100% of the physical information they consume. His 1976 paper from Cambridge University verified this permanent destruction of all cosmic data. However, this mathematical certainty suggests every atom in your body. Leonard Susskind watched in a San Francisco attic as Hawking's this elite gathering at Werner Erhard's home became a desperate war for the survival of modern physics. Stephen, sitting in his wheelchair with that characteristic slightly mischievous glint in his eyes, had just finished explaining why information, the fundamental bits that make up you, me, and everything we see, simply vanishes when it falls into a black hole. I remember looking over at Gerard Hooft, the brilliant Dutch physicist from Utrecht University who would later win the Nobel Prize in 1999. We were both stunned. It wasn't just a technical disagreement. It was a declaration of war against the very foundations of logic and the preservation of reality. You see, in the world of quantum mechanics, there is a sacred rule called unitarity. It is the law that says the past always determines the future, and the future always encodes the past. Information cannot be created, and it certainly cannot be destroyed. It is the gold standard of physics. To understand why I was so disturbed, think of the universe like a giant bathtub. If you throw a rubber duck into the water, you might create ripples and splashes, but those movements are determined by the duck's entry. If you burn a book, the information in the ink and paper isn't actually gone. It's just scrambled into heat, light, and ash. In theory, if you were a godlike observer with a powerful enough computer, you could track every single atom and photon to reconstruct the text of the book perfectly. But Stephen was proposing something far more radical. He was using the math of Einstein's general relativity to show that black holes were the ultimate cosmic paper shredder. According to his 1976 paper, Breakdown of Predictability in Gravitational Collapse, when a black hole eventually evaporates via what we now call Hawking radiation, it leaves behind only random thermal heat. No matter what you threw in, a library, a computer, or a human being, the output was always the same meaningless static. The information wasn't just hidden behind an event horizon, it was deleted from existence. As I sat there in that cramped, wood-paneled room in California, I realized that if we couldn't prove Stephen wrong, then the very concept of a fact would lose its meaning. We weren't just debating the properties of collapsed stars. We were fighting to save the objective history of the universe itself. This was the opening shot of the Black Hole War, a 20-year intellectual struggle that would force us to reconceptualize the very canvas upon which reality is painted. You see, to understand why Stephen Hawking's claim sent a shiver down the spine of the physics community, you have to understand the two giants that rule our universe. On one side, you have general relativity, Einstein's masterpiece. It's the physics of the big, the heavy, and the smooth. It tells us that space and time are like a giant rubber sheet, and gravity is just the curves and dips made by stars and planets. On the other side, you have quantum mechanics, the physics of the tiny, the jittery, and the discrete. It's a world of probabilities, coin flips, and uncertainty. For most of the 20th century, these two lived in separate neighborhoods and never really talked to each other. But in 1974, Stephen Hawking decided to force them into the same room, and the result was a theoretical explosion that threatened to bring the whole house down. It started with a paper in Hawking had been thinking about what happens at the edge of a black hole, the event horizon, when you take quantum effects into account. Now, think of the vacuum of space. Most people think it's empty, but the quantum truth, pairs of virtual particles, are constantly popping into existence out of nowhere, an electron and a positron, perhaps, only to collide and vanish a trillionth of a second later. Usually they cancel each other out so quickly we never notice, but Hawking realized that if this happens right on the edge of a black hole, something strange occurs. One particle might fall into the abyss, while its partner escapes into the cosmos. To an outside observer, it looks like the black hole is glowing. It's emitting what we now call Hawking radiation. This was a brilliant discovery. It showed that black holes have a temperature. It showed they aren't eternal. They slowly leak energy, mass, and heat into space. If you wait long enough, trillions upon trillions of years, a black hole will eventually shrink and completely evaporate into a puff of radiation. But then, in 1976, Hawking published a follow-up paper that was much more sinister: Breakdown of Predictability in Gravitational Collapse. This is where the war really began. Hawking argued that if a black hole evaporates and disappears, all the information about what fell into it, every book, every atom, every memory, in the world of general relativity, this isn't a problem. Einstein's theory has the no-hair theorem, which says a black hole only cares about how much it weighs, how fast it spins, and its electric charge. It doesn't care if you threw in a library or a truckload of coal, but in quantum physics relies on a principle called unitarity. It's a fancy word that basically means the sum of all probabilities must always equal 1. More importantly, it means that information is conserved. If you have the complete state of the universe right now, the laws of physics should allow you to work backward and perfectly reconstruct the past. It's like a cosmic law of cause and effect. If you burn a book, the information isn't gone. It's just scrambled into the smoke and ash. In theory, if you were smart enough, you could piece it back together. But Hawking was saying that black holes are different. He was saying they are a cosmic delete key. According to his calculations, the radiation coming out was purely thermal, random noise that contained zero information about the contents of the black hole. If the black hole disappears and the information isn't, this wasn't just a minor disagreement about star death. It was if information can be destroyed, then the laws of physics are not deterministic. The past can be erased, and the future becomes unpredictable. To people like me, this was a catastrophe. It meant that at a fundamental level, the universe didn't make sense. We were looking at a hole in the fabric of reality itself. Everything they believed up to this point was wrong. For me, sitting in that attic in 1981, listening to Stephen's soft, computer-generated voice explain why my life's work was built on a lie, I knew I couldn't let it stand. I had to find a way to save that information, or physics, as we knew it was over. For nearly a decade after the 1981 attic meeting, the physics community remained locked in a state of intellectual trench warfare. On one side, you had Stephen Hawking and the relativists, who argued with mathematical elegance that information was simply destroyed in the crushing singularity of a black hole. On the other side, there was myself and Gerard at Hooft, maintaining that such a loss would invalidate the very foundations of quantum mechanics. We were essentially shouting into a void, trying to find a mechanism that could explain how the bits of reality could survive the ultimate garbage disposal of the cosmos. The turning point didn't come from a new equation for gravity, but from a radical reinterpretation of a concept called entropy, first championed by Jacob Bekenstein. Bekenstein was a visionary who had suggested back in the 1970s that a black hole's capacity to store information was proportional not to its three-dimensional volume, but to the two-dimensional surface. Now think about how profoundly weird that is. If you go to the grocery store and buy a can of soup, common sense tells you that the amount of soup you get, but Bekenstein's work implied that in the case of a black hole, the soup, the information, is actually written on the label. If you try to add more information to the black hole, the can doesn't just get more crowded, the label grows. It was the loose thread that Hooft and I needed to pull. I remember sitting in my office at Stanford, wrestling with the implications. If the information is on the surface, then it never really enters the black hole in the way we think. It's encoded on the boundary. This led me to publish a paper in 1993 titled "The World as a Hologram," where I proposed what we now call the holographic principle. Imagine a standard credit card. On its surface is a small, two-dimensional plastic etching, a hologram. When you tilt it, you see a three-dimensional image with depth and structure. The image looks 3D, but everything required to create it lives on a 2D surface. Gerard at Hooft, that brilliant stoic Dutch physicist who would go on to win the Nobel Prize in 1999, was arriving at a very similar conclusion. We realized that if all the information about an object falling into a black hole is preserved on the event horizon, it could eventually be leaked back out as the black hole evaporates. It would be like a masterpiece painting being fed through a high-end paper shredder. The resulting pile of confetti looks like meaningless junk, but if you have a powerful enough computer and enough time, you could, in theory, reconstruct the entire painting. The information isn't gone, it's just incredibly scrambled. And that's when the real question emerged. If a black hole is a holographic projection, we began to realize that the holographic principle wasn't just a trick to solve a paradox in a distant corner of space. It was a fundamental law of nature. It suggested that our entire existence, this three-dimensional room you're sitting in, the distance between you and the wall, the stars in the night sky, might just be a projection of information encoded on a distant, two-dimensional boundary of the cosmos. We were effectively arguing that the depth of the world is an illusion, a beautiful phantom generated by a flatter, deeper reality. We had found a way to save the information from Hawking's paradox, but in doing so, we had fundamentally altered what it means for something to be real. We had the logic and we had the analogies, but the physics world is built on more than just intuition. It is built on rigorous proof. We were making a massive, reality-shattering claim, and we needed someone to provide the mathematical bridge that would connect these disparate worlds of gravity and quantum fields. We needed a miracle of mathematics to show that the information was safe once and for all. By 1997, the tension in the physics community had reached a boiling point. It wasn't just a friendly disagreement anymore. It was a fundamental rift in how we viewed the machinery of the cosmos. On one side, you had the quantum revolutionaries, Leonard Susskind, Gerard, Hooft, and a brilliant young physicist. On the other, the two giants of general relativity, Stephen Hawking and Kip Thorne. They decided to settle it the way scientists often do when the math gets too messy, with a wager. The terms were simple. If information was truly lost in a black hole, Hawking and Thorne won. If information was somehow preserved, Preskill won. The stakes, an encyclopedia of the winner's choice. It was a poetic choice of prize, wasn't it? An encyclopedia is the ultimate symbol of human knowledge, a collection of bits and bytes that, according to Hawking, could be deleted from the universe as easily as burning a book. But the tide was about to turn, and it wouldn't come from a telescope or a particle accelerator. It came from the mind of Juan Maldacena. Maldacena was a young professor at the Institute for Advanced Study, and in 1997, he published a paper that changed everything. He proposed something called the ADS/CFT correspondence. Now, don't let the acronym intimidate you. It's one of the most cited papers in the history of physics for a reason. Think of it like a holographic translation dictionary. Maldacena showed that you could take a complicated, gravitating universe, the kind where black holes live, and map every single thing happening inside it to a flat, lower-dimensional boundary that didn't have gravity at all. Imagine a soup can. All the complex swirling motion of the soup inside the can represents 3D gravity and black holes. Maldacena proved that you could describe every single detail of that soup just by looking at the label on the outside of the can. And here was the kicker. The physics on the label followed pure quantum mechanics. Since quantum mechanics requires that information is never destroyed, and since the label was a perfect mirror of the soup, the information inside the black hole had to be safe. It was a mathematical checkmate. But the most shocking, even with Maldaceno's proof, Hawking was a hard man to move. He was the commander of his own ship, and he wasn't going to abandon his paradox without a fight. It took another 7 years of intense debate, calculation, and the mounting weight of the holographic principle before the world's most famous physicist finally lowered his sword. The moment of truth arrived on July 21st, 2004, at the 17th International Conference on General Relativity and Gravitation in Dublin. The lecture hall was packed. The air was thick with the sense that history was being made. Hawking rolled onto the stage, and through his computerized voice, he made the announcement that he conceded. He admitted that he had been wrong for nearly 30 years. Black holes, he acknowledged, do not destroy information. Instead, they eventually release it, albeit in a scrambled, mangled form, like a book that has been through a paper shredder. You can still read it, but you're going to need a lot of patience. Keeping his word, Hawking presented John Preskill with the chosen prize, Total Baseball, the ultimate baseball encyclopedia. He joked that he should have perhaps given him the ashes of an encyclopedia instead, given how difficult it would be to recover information from a black hole's radiation. But the gesture was profound. One of the greatest minds in history had been proven wrong by his own peers, and in doing so, he helped us uncover a deeper layer of reality. The black hole war was over, but the victory wasn't just for Preskill or Susskind. It was a victory for the consistency of the laws of physics. We had saved the past from being erased. We had ensured that the universe, however strange, remains a place where cause leads to effect, and where the story of every particle is written in stone, or perhaps on the holographic boundary of the stars themselves. This concession didn't just end a debate, it opened a doorway into a new era where space and time are not the fundamental ingredients of reality, but rather things that emerge from something much deeper, information itself. So, where does this leave us? You might be sitting there, perhaps in a lecture hall or late at night with your laptop, wondering why this decades-long intellectual brawl over a baseball encyclopedia actually matters to you. After Stephen Hawking stood on that stage in Dublin in 2004 and admitted that he'd been wrong for nearly 30 years, the world didn't stop spinning. But for those of us who spend our lives staring at blackboards, the very ground beneath our feet had shifted. The black hole war wasn't just a spat between two brilliant men, it was the moment we realized that our common sense view of the world, the idea that objects exist here or there in three-dimensional space, is likely a magnificent illusion. Think about the holographic principle that Gerard at Hooft. It tells us something deeply unsettling. If every bit of information that falls into a black hole is perfectly preserved on its two-dimensional surface, then the three-dimensional inside of that black hole is just a projection. But gravity is universal. If it works for black holes, it must work for the room you're sitting in right now. It means that you, your chair, and the stars in the sky are potentially just a 3D image projected from a 2D boundary located at the very edge of the observable universe. It's like a soup can. All the delicious complex ingredients are inside the volume, but every single bit of fundamental information about that soup, the calories, the sodium, the list of ingredients, is printed on in this new physics, the label is what's real. The volume is just a trick of the light. Since the resolution of the paradox, theoretical physics has moved toward the idea that space-time. Instead, we now suspect that space-time is emergent, something that bubbles up from the deeper, darker waters of quantum entanglement. When Juan Maldacena showed us the ADS/CFT correspondence in 1997, he gave us a mathematical bridge between a world with gravity and a world without it. He showed us that the complex dance of particles on a boundary is mathematically identical to the physics of the interior. This was the peace treaty of the Black Hole War. It proved that unitarity, the sacred law that information can never be destroyed, is preserved. However, science never truly sleeps. Just when we thought we had solved Hawking's paradox, a new generation of physicists, Almeri, Marolf, Polchinski, and Sully, proposed the firewall paradox in 2012. They suggested that if information truly escapes a black hole, an observer falling in might be incinerated by a wall of high-energy particles at the horizon, which would mean Einstein's equivalence principle is wrong. The war hasn't ended, it has simply moved to a new front. We are still grappling with the same haunting question. How can the laws of the very small and the laws of the very large? What Leonard Susskind and Stephen Hawking taught us is that progress in physics requires a certain kind of stubbornness, a willingness to protect the laws of nature even when the greatest minds in the world tell you they've collapsed. We learned that the universe is far more interconnected than we ever dreamed. Information isn't just a sequence of bits. It is the fundamental fabric of reality. It can be scrambled, hidden, or smeared across the horizon of a dead star. The legacy of this conflict is a universe that is far more mysterious and far more beautiful than the one Newton or even Einstein imagined. We are living in a giant, quantum mechanical hologram, trying to decode the static on the screen to understand the film. It's a humbling thought, isn't it? That we might be nothing more than a projection from a distant boundary. But even if we are just ripples in a holographic field, the fact that we can use our minds to reach out and touch the edges of the cosmos is nothing short of a miracle. The universe is not only stranger than we suppose, it is stranger than we can suppose. If this journey through the mind of a genius left you thinking, subscribe and hit the bell. Tell us in the comments.